Now, in this video, we are going to consider the polar section modulus. The moment of inertia about an axis perpendicular to the plane of an area is known as the polar, that is, moment of inertia, which is Jp. Polar moment of inertia may be calculated as the sum of moment of inertia about two mutually perpendicular centroidal axes in the plane of section. So that means for solid shaft, Jp will be equal to, it is sum of the polar moment of inertia about xx and yy axis, that is Ixx plus Iyy. That is the moment of inertia about the Ixx will be equal to pi d to the power of 4 by 64 plus moment of inertia about the yy axis will be again, which is plus pi d to the power of 4 by 64. So on addition, you will going to get it as pi d to the power of 4 by 32. So from the torsional equation, what we have is T by Jp will be equal to tau by R, where tau max or tau will be equal to maximum shear stress at the outer surface, and capital R equals extreme fiber distance from the center. So therefore, T will be equal to Jp by R into tau, which will be equal to tau into Zp, where Zp will be equal to polar section modulus. So hence, what is the definition of polar section modulus? The polar section modulus is defined as the ratio of polar moment of inertia to extreme radial distance of the fiber from the center. Now for solid circular shaft Jp, that is, or J will be equal to pi d to the power of 4 by 64, and capital R will be equal to d by 2. So polar section modulus Jp will be equal to Jp by R, which will be equal to pi d to the power of 4 by 32 by d by 2 will be equal to pi d cube by 16. So therefore, for a hollow circular shaft, polar section modulus will be Zp, which is equal to Jp by R, which will be equal to pi by 32 into d naught to the power of 4 minus di to the power of 4, and to the distance of the extreme fiber, which is d naught by 2. So on simplification, you will going to get it as pi by 16 into d naught to the power of 4 minus di to the power of 4 divided by d naught. Here 32 and 2 will go cancel, which will become 16. So pi by 16 into d naught to the power of 4 minus di to the power of 4 by divided by d naught. Now from torsion equation, T by Jp will be equal to tau by R. Therefore, T will be equal to tau into Zp, Jp by R, which will be equal to tau into Zp. So where Zp will be equal to polar section modulus, which is in mm cube. So now the next we're going to consider the torsional rigidity. So let twisting moment T produces a twist of theta in radians in length L. So from torsion equation, T by Jp will be equal to G into theta by L, where theta will be equal to T into L by G into Jp. So hence for a given torque T and length L, the twist is inversely proportional to G into Jp. This product G into Jp is called torsional rigidity of the shaft. That is, torsional rigidity is the torque required to produce a unit radian of twist in a unit length L. It is also known as the torsional stiffness. Torsional rigidity of the hollow shaft is more than that of the solid shaft. So the torsional stiffness or the torsional rigidity, which is Kt, which will be given by T by theta, which will be equal to G into Jp by L. So from the torsional strength, if you are considering, the torsional strength is defined as the torque per unit maximum shear stress. It is also known as the efficiency of the shaft. Therefore, the torsional strength, which is T by tau, will be equal to the torsional strength, which is equal to T by tau. From torsional equation, T by Jp is equal to tau by R. T by tau will be equal to Jp by R, which is equal to Zp. Therefore, it may be represented as the polar section modulus. Now we are going to take up one more property, which is the torsional flexibility. It is the reciprocal of the torsional rigidity, that is, torsional flexibility is the angle of twist per unit torque. So therefore, the torsional flexibility is given by L by G into JP, which will be, so when we are considering the shear stress distribution, the maximum shear stress, which is tau max or tau induced in the surface of the shaft, is equal to the allowable shear stress for the shaft material. So in a solid shaft, the maximum shear stress will be induced at the outer surface and zero at the inner surface under the center at the peak load condition. This ill effect can be overcome to some extent by replacing the solid shaft by a hollow shaft of same torsional strength. That means if you see here in the equation, that is in this figure, in the solid shaft, you have the maximum shear stress at the outer surface and minimum, that is zero, at the center of the solid shaft. This can be overcome by replacing with a hollow shaft wherein the maximum will be at the outer surface and the minimum at the internal surface or internal diameter, wherein you will going to get the minimum shear stress. Where here in this case, it will not be zero at the center. So this is how you will be able to analyze the shear stress. And also the torsional moment of resistance, which we are considering now, it is the maximum torque that can be carried by the section without exceeding the maximum permissible shear stress. It is the sum of the moments of tangential shear stress acting on any transverse section. It is denoted by TR. Therefore, the torsional moment of resistance TR is given by Zp into tau, where Zp is called the polar section modulus, where tau is the permissible shear stress. So for a solid circular section, TR will be equal to pi by 16 into tau into d cube. So for the hollow section, pi by 16 into d naught to the power of 4 minus di to the power of 4 by d naught into tau. So where tau is the maximum shear stress or the maximum allowable shear stress, and d will be equal to the diameter of the solid circular shaft, and d naught is the external diameter of the hollow circular shaft, and di will be equal to the internal diameter of hollow circular shaft. So by considering from the strength and the rigidity criterion, how we are going to define this? So considering from the strength criterion, according to this criterion, the maximum shear stress, which is tau or tau max, induced on the outer surface of the shaft should not exceed the permissible value. So when you're considering that, hence the relation used for this criterion is T by Jp is equal to tau by R. Therefore, T by tau will be equal to Jp by R, which is equal to Zp, where T will be equal to tau into Zp. So from the solid circular shaft, MT or torque will be equal to pi d cube by 16, and Zp will be equal to pi d cube by 16. Now similarly for a hollow circular shaft, MT or T will be equal to pi by 16 into d naught to the power of 4 minus di to the power of 4 divided by d naught into tau. So where Zp will be equal to pi by 16 into d naught to the power of 4 minus di to the power of 4 divided by d naught. So knowing T and tau or tau max, the diameter of the shaft can be found. Similarly, from the rigidity criterion, if you are considering, so here, according to this criterion, the diameter of the shaft is calculated based on the given value of angle of twist, theta. The angle of twist theta is specified as not to exceed a certain value, theta maximum, in a certain length. So the relation is T by Jp is equal to G into theta by L, where theta for solid circular shaft, J or Jp is polar, that is pi d to the power of 4 by 32. And for a hollow circular shaft, Jp will be equal to pi into d naught to the power of 4 minus di to the power of 4 divided by 32. So the required polar moment of inertia can be ascertained for the stiffness criterion. The diameter of the shaft can be determined from the value of Jp. So this is how you will be able to analyze the shear stresses and also the finding out the diameter from the torsional strength criterion and the rigidity criterion. Thank you.